Hello, everyone, and welcome to our webinar in which we will visit San Francisco State University and learn about their approach to teaching dynamics and vibration courses using modern pedagogy and technology. My name is Susanna, and I'm your Quanser host today. And now I would like to pass the microphone to my colleague and today's moderator, Peter Martin. Peter is an engineering curriculum manager at Quanser. His team develops course materials and also tools that help improve ways how courses are delivered. Peter?
Hello. Thanks very much for allowing me to moderate this session, and thanks again to Dr. Zhaoshuo Jiang for agreeing to do this session with us. I'm looking forward to his presentation. Dr. Zhaoshuo Jiang, as we said, is from the San Francisco State University, where he holds a PhD in civil engineering. Before his position as assistant professor, he worked at a number of industrial positions, including being a professional engineer in both Connecticut and California, where he worked on both low-rise and high-rise projects. And his current research interests at the university are in smart structures, structural control and health monitoring, and, as you'll see today, innovative engineering education. Without further ado, thank you very much, Dr. Zhaoshuo Jiang.
Thank you, Peter, for the introduction. And let me share my screen. All right, so it's my pleasure to be here. Oops, let me change that. Let's jump right in the presentation. So here is the outline of what I'm going to talk about today. First, I'll briefly introduce the motivation behind this project and our proposed solution to overcome some of the challenges in the learning using the latest technology. After that, I will show you some preliminary results on the implementation of our proposed solutions and end the presentation with some summary and future direction of the study. Engineering is an applied science. Combining theory, practical example, and hands-on experiments has proven to be effective in creating an active learning environment. However, they are not always available, especially for the physical experiment, due to many constraint factors such as lack of equipment, limited room capacity, conflict of testing schedule, accessibility of the facility, and safety consideration. To resolve this problem, researchers developed virtual laboratory. As an example, in a simulated laboratory, the experiments are modeled through computer simulation. Although it provides a meaningful experience to help students understand and learn important engineering concepts, assumptions have to be made in the modeling process. Therefore, it might not be able to fully replicate the actual experiments. Some researchers moved one step forward to develop the remote laboratory, where experiments are conducted by sending commands remotely to activate equipment. In the meanwhile, the data are streamed back to the students' computers. It offered the students the opportunity to participate in physical experiment remotely, but students need computers and specific software to access the experiment. And typically, it is very costly to develop and maintain the software. In addition, as inherently with the virtual laboratory, both of them could create a passive and isolated learning environment where the experience is confined to computer screens. And this denies students' ability to interact and communicate with the surroundings. And before I show you our attempt solution on this issue, I would like to do a small poll and see if you're ready for this. All right, here is our first poll. I would like to know, do you own a smartphone, a smart portable device? For example, the smartphone, tablet, and I give you a few seconds to respond. All right, team, if the response comes in, let's show the results. Oh, so we have 100% of the respondents saying they own a smartphone or tablet. Okay, great. And let's take a look at the second one. The second one is, will you feel uncomfortable if your smartphone is running out of battery when you just started a day? Again, let's spend a few seconds to give you some time to respond to the poll, and we'll come back with the answers. All right, let's take a look at the answers. Okay, we have 73% of you saying, you will feel uncomfortable if your phone is running out of battery, and 27% of you saying, no, I'm good. All right. And according to the poll, 100% of you saying you own a smartphone or tablet. With our smartphones, here is a scene that we often see on the dinner table nowadays, which you might be familiar with. Our phone seems to be our only friend on the table nowadays. And before eating, I don't know how many of you will take a food selfie. And being asked if you feel uncomfortable if your smartphone is running out of battery, 73% of you say yes. And these two students definitely feel the same. The boy on the right found outlet on the ceiling, and he managed to put the chargers in it. And the girl on the left found a place to charge her phone beside a tree. And she probably would need to stay there for a little while. And here is our upcoming generation. In order to keep them quiet on a dinner table, giving them a tablet might be an efficient way. The point to make here is that the younger generation grow up with these mobile devices. In addition to use them for entertainment, why not utilize this technology for learning? And with that, our proposed solution is to make all these critical elements in learning more accessible through the use of mobile apps. And to develop these mobile apps, we use qdex. qdex is a mobile development platform provided by Quanser, and it aims at transforming conventional learning environments with the use of interactive apps. One unique feature that we think is awesome is that the app developed through the platform are compatible with both iOS and Android devices, meaning that we just need to develop the app for once, and it can be run for both iPhone, iPad, or any Android device without further modification. From our personal experience, it has been a fast learning curve in developing the application using the platforms. And I'm going to show you in a few minutes some apps that an undergraduate student who has no prior coding experience developed in a few months. By harnessing the power of mobile technology and Internet of Things, we are able to develop a mobile laboratory, which allows students to remotely conduct physical experiments through their smart mobile devices. And by using devices that they carry with them every day, now they can access the learning materials anywhere at any time without the need of additional software and hardware. Also, a telepresent robot is integrated with the mobile lab to provide a real sense of participation. And I will talk more about it in the next slide. Here is the schematic of the mobile remote laboratory, in which we use an earthquake simulators, or so-called shake table, as an exemplar for the equipment being controlled. The user will first reserve a time to conduct the experiment through a booking system. With a unique access code automatically generated and sent by the booking system, the experiment will be initiated by sending over a control command from the mobile device. The command will be passed to the control PC to control the shake table. The measure data will be passed back to the control PC and then streamed back to the mobile device in real time. A telepresent robot is utilized to eliminate the passive feeling that might have in the virtual environment and to actively engage user by providing a real sense of participation. With the robot, students can move around, view the experiment from different angles. For example, they can communicate with the surrounding and even modify the experiment with the help of a lab assistant. Remote switches are set up in case of the unexpected system failure. If that happens, we can reboot the whole system through simply a tap on the apps, and the system will be back online within a few minutes. The shake table system, the shake table in this system was designed and built by Quanser for the University Consortium of Instructional Shaketable, or the USIS, which was established by Professor Charlie Dyke. It has an operation frequency of 0 to 20 Hertz with a peak acceleration of plus and minus 1G. One good thing for this is it provides a native control through MATLAB Simulink as well as LabVIEW, which offers a great flexibility to interact with other devices and equipment through the standard internet protocol. And building upon the remote lab, we developed a standalone learning module for dynamics and vibration courses to teach students on concepts such as equation of motion, frequency response, and resonance. And it is developed upon a past successful users module. The module consists of 3 interactive components, namely analysis, simulation, and experiments, representing theory, practical example, and physical experiments. The analysis component is designed to help users learn necessary background theory. The simulation component allows users to simulate the experiment to deepen their knowledge and also to explore new ideas without worrying about breaking the test structures or expensive equipment. The experimental component then provides the opportunity to verify their findings and experience the challenges in the real-world testing. The results from various components will be verified at different stages of the learning process, as indicated with the red arrows here. And to demonstrate how it works, let me show you a live demo here. I'm going to switch to my iPad here. So here is a live mirror of my iPad screen. Now I'm going to launch the qdex Plays, which hosts all the apps that we developed. I'm going to tap on the qdex Play apps on the right bottom corner here. And the first app I'm going to show you is called the Vibrations. I'm going to tap on that to launch the app. It is like a table of contents to connect the different apps in this module. And as you can see, we have 3 components, which are analysis, simulation, and experiment. When users tap on the more information buttons underneath that component, a brief introduction will show up and the button will change to Go To app. And the second tap will bring the user to the corresponding app. Now I'm going to launch the analysis app by tapping the Go To app. In the analysis app, a one-story building model, which is also called a single-degree freedom structures in engineering world, is used to help students learn fundamental concepts. Information on various components of the structure will be provided to calculate necessary property to derive the mathematical representation of the structures. Now, by tapping the different elements, detailed information will be displayed. And to look closer, simply tap on that figures will enlarge it for you. And you can go back to the app by tapping the Done button on the top right corner. And I'm going to do that. Now, the students can input those information in the field below to calculate the corresponding properties, such as, for example, the natural frequency of the structures. Now, by swiping from right to left on the screen, user can access the second page of the app. And this page contains an animation of a free vibration experiment. Now I'm going to tap on the Start Animation button there. This provides the user with the real-world scenarios on how to obtain this experimental data. And throughout the apps, there are links that allow students to get more information on that particular topic. For example, by tapping the help link beside the damping ratio, which I'm doing right now, it will bring the user to a help apps, which theories are explained in details. This would be helpful for users who are struggling with the concepts, and it is like a textbook in your pocket. User can go back to the previous app by tapping the arrow in the top left corner. Now I'm going to do that to go back to the analysis app. User can go back to the vibration app by tapping one more time to the left-hand corner. Now I'm going to tap on the button underneath the simulation app logo twice to go to the simulation app. I just want to point out Each of these apps can also be launched directly from qdex. After learning the necessary background knowledge from the analysis app, the simulation app here allows user to simulate the experiment. This will allow the user to explore and deepen the knowledge, and they can try all sorts of interesting ideas without worrying about damaging the expensive equipment. And in this app, user is able to excite the same single degree of freedom structure with various types of ground shaking. Now they can vary 3 different properties, the forcing amplitude here, the forcing frequency here, and the duration. Now the start button will enable the structure to move, and I'm going to tap on that right now. The displacement movement from the top of the structure and the ground will be plotted on the plot, with the blue series represent the top of the structure and the red series represent the bottom of the structure. And some parameters can be changed while the simulation is working so that the user can see the real-time effects on the structures. Let me try again. Now, if I vary, for example, the forcing frequency, you can see the structure is changing in real time. And if I try to hit its natural frequency, you can see the vibration is getting much larger. By swiping from right to the screen, now the user can go to the second page of the apps. Here, user will be answered questions related to the theories and the observation from the simulations. And instant feedbacks will be provided to the user. For example, if I check 8 on the answer and it's telling me the answer is incorrect, and it points me to the correct directions to find out the correct answers. Once all the questions are answered correctly, a bonus sliders that control the damping ratio of the structure will be visible from the first page. Now let me get all the correct answer and show you that. Now, once you've done all the answers correctly, when you go back to the previous page, another slider called the damping ratio is show up, which is not there before. This gamification aspect is designed to provide a fun learning experience for the students. Now I'm going to tap on the vibration on the top left corner to go back to the vibration app. A numerical model is a valuable tool for students to observe the response of the structures. However, it might not be able to fully represent the accurate real-time or real-world behavior due to factors such as modeling error, assumption being made, and uncertainty in testing. In the experimental component, user will be given the opportunity to test a real single degree of freedom structure on a shake table. And I'm going to launch the experimental app now. The first thing the user will see is an animation of the building that will sway when the user shakes their mobile device. You cannot see me, but I'm actually shaking my iPad on my hand right now. And the amount of deformation of the structure is based off the readings from the device accelerometers, which is a sensor that monitors the motion of the device. And this is a good example on how qdex allows developers to fully utilize the sensor in the mobile device. And as you can see, there are people in the building that are scratching their heads because earthquake's coming. And this page also contains more information on the mobile remote laboratory. The user can expand the section to show more information by tapping the title there. Before conducting an experiment, the user will just need to reserve a time through a booking system. And user can access that booking system by simply tapping on the highlighted tab on the booking system link here, which I'm going to do it. Now, it brings us to the booking system website, which they can reserve a 30-minute time slot. And the booking system ensures that only one user can access to the control of the shake table at a time. Now, if you tap on any of the available time slots, it will ask you to input some basic information as shown here. Once they do, and unique access code will automatically be sent to the users. Now I'm going to switch to my mail apps to show you what is a typical email look like. The email will say, hey, thank you for making reservation, and the access code for the experiment is blah, blah, blah. The user can simply copy that access code there. Let me do that. Copy, and go back to our qdex app there. By swiping to the right on the screen, it brings you to the second page of the apps, and there you can input your access code and check the access code, the check access code button there. Once the correct access code is entered, the user now have control of the shake table. On the top left corner, a timer will display the remaining time that the reservation is left. Now I only have 9 minutes, so I probably should be quick. And once the user gain control, there are 3 command signals they can choose from: sideway, side sweep, and earthquake. And let's check out the sideway. User now will be able to adjust the frequency, amplitude, and duration of the sideway, same as the simulation. Now, let me first choose the design frequency and design amplitude. When I hit send, the shake table will move. And in order to provide user a real sense of participation, a telepresent robot is adopted and integrated into this remote laboratory. And this robot allows for unique and immersive experience for the users. Now I'm going to rotate my device for 90 degrees. And I will bring the robot app side by side with the experiment. Let me adjust the width and log in. All right. Here we go. And this is a live shot of the lab. And user can control the robot. You can, turn left, turn right. You can move forward. You can move backward. You can just go around the lab. And you can view the experiment from different angles. The user can also speak with the lab assistant if someone's there to physically modify the configuration with the help of the lab assistant. Now, once I tap this send button in the control panel on the left side, the command is going to be sent to the control PC to activate the shake table. And now I'm going to do that right now. Let me back up my double a little bit so that you can have a better view. And send. And the measured data from the accelerometer is streaming back to the mobile device in real time. The red series here is the acceleration from the top of the structure, and the blue series here is the acceleration from the accelerometer mounted on the shake table. In the top left corner of the screen, there's the top right corner, there's a string of tests that letting the user know about the status of the shake table system. Now it's telling me the system is ready to go again. Okay, let me close my double and only show you the experimental apps. I can now go to the third page of the app by swiping from right to left on the screen. With the computational power of the mobile device nowadays, the app is capable of performing some very sophisticated analysis, such as the frequency response analysis or the FFT. Now, when I tap on it, the result just comes out. In addition, the measured data can also be sent to the user through emails for further analysis. For example, if you want a student to turn in the homework, they need the data to do that. And this concludes my demo. And let me bring you back to the presentation. The mobile learning module was first implemented in a senior level course here at San Francisco State University in 2016. And the results we got were very promising. And with that encouragement, we refined the module according to the students' feedback and expand the effort to 3 different dynamics and vibration courses at 3 universities in last year. And for the purpose of maintaining the confidentiality, we'll refer to 3 universities as University A, B, and C, and the corresponding courses as Course 1, 2, and 3. These universities are carefully selected to evaluate the adaptability and expandability of the module. Also, we would like to evaluate the module's effectiveness in advancing the learning of students from various backgrounds and knowledge levels. Course 1 at University A is a junior level required course for all architectural engineering and civil engineering majors. And we have 72 students in the fall 2017 semester. Course 2 at the University B is a senior level civil engineering core course. and there are 33 students enrolled in that particular semester, while course 3 at University C is a junior level mechanical class with 49 students enrolled in that quarter. Pre and post survey are given to a student right before and right after using the module to see its effects. The characteristics of the student are listed here, but I'm not going to go into details. One unique attempt I'd like to mention for University A is that appropriate modular components were chosen to form the two submodules, and they are released to students at different stages of the class, while at University B and C, the whole module is sending in as one. 3 measures, namely Smart Tablet Readiness Measure, or Smart Stream, Engineering Concept Self-Efficacy Test, SSAT, and Engineering Concept Achievement Test, ECAT, were developed to assess the mobile learning module on student learning. Smart Stream is a self-report measure to collect students' preference on using smart mobile device for learning. SSAT is a 5-point Likert scale self-efficacy test to evaluate the ability of students to learn concepts and perform tasks efficiently. ECAT is a 4-point scale knowledge test to assess student learning in engineering concepts. In Smart Stream, we ask questions to evaluate students' readiness for mobile learning. For example, we ask, do they own a smart mobile device? If not, are they planning to get one in the near future? For those who have the mobile device, how often do they use them for entertainment, obtaining information, and learning activities? And here are some results. This chart showed the total response of the student in all the 3 universities. Not surprisingly, students reported that they use mobile device for entertainment and obtaining information the most. But we can also see that using the mobile device for learning activity is getting close. To give you an example, if we summed the percentage highlighted in red, we have 99% of the respondents that they use the mobile device for entertainment for more than several times a week. And 94% of them use it for obtaining information more than several times a week. For learning activity, we have 74%, which shows that using the mobile device as a learning tool is pretty common to students nowadays. If we take a closer look at using the mobile device for learning at the 3 different universities, there are 59% of students at University A and C use mobile device for learning in more than half of their courses. And at the University B, has up to 86%. This further demonstrates the readiness of using the mobile device for learning among students. To evaluate whether the mobile learning module helped increase student self-efficacy, we ask them questions such as if they are confident that they have the ability to learn materials on various concepts, if they think they can do well on exams, if they can explain the concept to others, if they think they can understand the topic build a point of knowledge, and if they think they can do well on the lab. And due to the time, I'm going to just show you the results for University A as an example, giving us a larger sample size. For University A, we evaluate the student's self-efficacy in frequency response and damping and resonance. Increase in students' self-efficacy with statistically significant is found in all the questions we ask. This really demonstrates increase in students' self-efficacy on these critical engineering concepts, and also demonstrate their confidence on moving forward to more advanced knowledge. And to evaluate whether the mobile learning module help increase students' knowledge competence, we ask them questions on various concepts aligned with the course objective. So different courses will have different evaluation interests, therefore different set of questions. And this slide showing you 5 questions for course 1 at University A that we asked. We asked them about equation of motion, damping ratio, relationship between excitation frequency and response of the structures, and data measurements. They are giving options of, I don't understand the statement, I understand the statement, but I don't know the answer, the statement is true, and the statement is false. From the results, we observe difference with statistically significance in 2 out of the 5 questions, and both of them show increase in students' knowledge competence. In addition to those 3 measurements, the user experience on the developed apps has also been investigated through a series of post-survey questions. And as shown here, the feedback is very positive as well. And by the way, these are the average results from all the 140 participants from the 3 universities. And you know how critical the undergraduate student could be. And 76% of the respondents found the apps is easy to use. And 83% felt that the assistant, including the help link, recorded videos, and lab assistant was provided in a timely manner. It's really outstanding to see that 89% of them agreed that the apps help to improve their understanding on those critical concepts. And this is another indicator from the student perspective to show the increase in their self-efficacy. And in total, 81% of the respondents said they would recommend the learning module to a friend. To wrap up, in this study, we attempt to use the mobile learning as a tool to provide students greater access to theoretical knowledge, practical example, as well as the physical experiment. And the results from this study demonstrate its potential to increase students' knowledge competence as well as the self-efficacy. The results are from different university implementations show variations. It seems that dividing the module into sub-modules and provide them to a student at a different stage will help students better understand the concept, but further study will be carried out to look into it more. We just got the data back and we're still under the process of post-processing the data. And it will be interesting to see in the future how the mobile laboratory platform could be used for other equipment, and to look at its potential influence to the general public with the various backgrounds. And we are making the mobile learning module and the remote shake table laboratory available to you. For those who are interested in checking them out, here are the links for the information videos that we have, and as well as an instruction on how to make a reservation to try out the remote lab yourself. If you'd like to know more about what we have done, here are some publications we have on this so far. And we will be presenting the detail of the study shown in today's webinar in the upcoming 2018 ASEE annual conference in Salt Lake City this year. And here I would like to thank the faculty member from the 3 universities in the implementation process. Also, I would like to acknowledge our partner in Quanser, the Idea Center, the CSU course we designed with technology program. That is the time that we start this laboratory there, and COSI and School of Engineering at San Francisco State for their support in this project. And that's all.
All right. Well, thank you very much, Dr. Jiang. I really appreciate seeing all this. And again, it's always amazing to see what you guys have done. And from the qdex perspective, we really appreciate the work you've been doing to sort of promote and to push the platform forward, as well as to validate the approach that we've been taking with the platform and what's capable with what we've built. At this point, we'd like to open up to Q&A. If anyone has any questions for Dr. Jiang, then we're happy to pass those along. Okay, well, we have our first one here. One of our listeners is interested if your platform that you've built, the ability to interface your shake tables, is that open to other hardware platforms, or is it unique to the shake tables that you have?
Well, when we try to build a platform, we try to be generalized. The communication between the shake table and the platform is through a TCP/IP protocol, which is a very common protocol that used to communicate between devices. So I would say it has the potential to communicate with the other platform as well. That's the next step that we're interested in looking into.
All right. We have another here. Was the data for competency compared to students who didn't use the app?
Meaning the control group and experimental group. We do not have that information on this particular implementation, but we do have some comparisons on another university implementation, which I didn't show in this presentation. And from that result, we see increase in different areas as well. Yes, and then that demonstrates the potential of the platform as well.
Okay, we have one other here. One of our listeners is interested in whether it's possible to add additional functionality to your system and how easy that is in terms of not just the sine waves and some of the characterization of the platform and earthquake profiles, but if that can be expanded to do other types of remote applications, maybe a little bit more customized to their interests.
Absolutely, and as I mentioned a few minutes ago, we're trying to standardize the platform, and it could be easily add the different other components into that control panel as well.
All right, it looks like that's all about all the questions we have at the moment. So just from the qdex side, I wanted to take just a little moment to slightly self-promote the platform. We've been working with Dr. Jiang and his partner for, I was just talking to my colleague, since the beginning of 2016. So it's been a very, very successful relationship. As I said, we really appreciate all the hard work they've been doing to build out the platform and to help us make something that has usage outside of the conventional e-learning platform. If you're interested in learning about qdex and for trying your hand at creating content and developing materials for your courses and your interests and subject areas, we are launching the platform next week. Perfect timing. On Monday, we'll have our new platform rolling out, and that'll be complete with our website at, you can see here, qdexapps.com. The website currently, if you go, is still relevant to qdex, but it will be updated this weekend to relate to the platform that we're launching in terms of our public offering. In terms of how that works, you're able to always create content for free. So we're never going to charge for creating content. We want to be able to have you create as much content as you like. If you're going to share it with your students or with your colleagues, at the moment, it's $1 per student or per colleague per month. So it's a very low price for sharing and for using the platform as a way to distribute your content. And you'll find at the website there's lots and lots of resources for getting to know the platform, for getting oriented with how the system works, how to create your own content. And there's a forum and chat and all different ways you can reach out to us to get a little bit more help if you need it and to get a feel for what's possible. So I'd encourage you to give it a try and to sort of take this in a totally different direction. We never conceived of our platform as being used in this kind of application that Dr. Jiang and his team have done. So if you have an idea for something you think is possible, but you don't know how to do it, I'd encourage you to try qdex and see if that's a perfect fit for what you'd like to do. And with that, I'll pass back over to our host, Susanna.
Thank you, Dr. Jiang, for this great presentation and sharing your ideas on how to develop a really engaging and effective engineering course, a course of the future. Thank you, everyone, for joining us today. As I mentioned, we recorded the webinar, and we will share the link with you within a few days, so you can revisit it or share it with your colleagues. Our next Quanser user webinar is coming up at the end of the March. Coincidentally, it will be, again, tied to civil engineering and shake table systems. This time we will visit the University of Rijeka in Croatia, where they will talk about their teaching activities and also very interesting research focus on dynamic response of discontinuous systems and behavior of structures under multi-support excitation, so something like long bridges and how they behave in an earthquake. So we are hoping that you will join us again for the next presentation. And again, thank you everyone for joining us today.